Question number 9. A sound wave with a frequency of 200 hertz and a distance of 100 meter, okay, was cut off in 0.5 seconds. Then what is its wavelength? Okay, now we need your support, guys. Now just try to solve it quickly and we will see the answer here.
Sir,
yes,
I think, sir, we should use V equals delta D over delta T, which is 100 over a half, which is 200. That's the velocity. And then plug it in the second equation, which is frequency equals velocity over wavelength. I mean wavelength equals velocity over frequency.
Okay. So what's the answer?
So it will be 200 divided by it will be 200 divided by 200, which is 1 meter. So C.
Ah, great. Yes, you're right. Exactly. Your answer is right. Nice. So our colleague that says that what's happening here. So I will just solve it now. Okay. Now we have here, this is the frequency. So let's just write the given data here. This is F equal 200 hertz. Okay, and the distance of this distance, which is D, which is 100 meter. And there is a time also. You see now that if you just get the given data, things will be clear for you. Then you will understand which formula you will use. Okay, so now we have a frequency and we have the distance and we have the time. We are asked to find the wavelength. Okay, look, there is something that you have to follow actually. You see that the parameter that the question asks about, just write the formula. Okay, try just to memorize this formula. This, it's equal to velocity over frequency. Okay, so this is the formula. So now we have the frequency. Frequency is already given, but now velocity is not given here. Sometimes some questions, as we have said, that you will use 2 steps to solve it. So there is another step that I have just to do, which is what? To find the velocity. Okay, let's draw a line here. Okay, so velocity will be what? As we know from mechanics, it is distance. Yes, you're right, Siba, you're right. Over time, which is what? 100 over 0.5. Okay, let me just write 0.5, which is half in another form to make it easy. Oops. Yeah, 1 over 2. And as we know from mathematics that the denominator of the total denominator will go up here, will be multiplied with the numerator. So it will be what? V will equals 2 times 100. Will equal how much? 200. And with the unit actually. Anyway, it is meter per second. Okay, so now we get the velocity. Fine. So now let's find the wavelength, how it will be. Now we have 200, the velocity, over the frequency. How much frequency we got? From the question, it is 200 hertz. So it is what? It is 1. Yes, you're right. And the wavelength is by the metric unit, or meter, by meter, you can say, or by length units. And the SI unit, as we say, it is meter. So it will be meter. So the answer is C. Fantastic. Nice. Okay. Question number 15. The shortest length of a tube to resonance at a given frequency. Shortest. Okay. Is satisfied by a tube. That is a quarter of the wavelength. Okay. Maybe the question is not clear. I think. But in any question itself, the answer is there. It's just okay. Hamza, mashallah. Yes, Hamza, you are right. It is A. Yes. Why here's just mentioning as as a written quarter of the wavelength. You see that's the lowest and the shortest, as we mentioned. We saw before that in the table, either we have half wavelength, or maybe we have fourth quarter, or fourth wavelength, and so on. But the lowest that we see is quarter, isn't it? The lowest wavelength is a quarter. okay, which is this one. Let me just go back quickly, very quickly now. Here, where is that table? Yeah, you see, this is the lowest one. Can you see any other lowest than this? No, it's the lowest one. So it is a quarter. He's asking about this. What is the shortest wavelength among the tubes? This is the explanation of the question, actually. Where are we now? Yeah, here. Yes, shortest length. Okay. So he's stating a quarter of the wavelength. So it will be what's A, which is a quarter. Now let's go to this question. Okay, now that we have a little calculation here, what is the frequency in hertz? Now we are asking about the frequency of the second resonance for a one end. Okay, we are asking about end closed tube that has a height of 15, knowing that the speed of sound is how much? 343. Okay, what we are given here, first thing that we are given the L. This is the height of the tube itself, which is L. This is the first thing. Second thing, we are given the velocity of the wave itself, which is sound. Now they are just trying to make experiments on the sound waves, okay, using these tubes to understand the behavior of the sound wave. Okay, now we are asked about to find frequency, which is F. Okay, Hamza is saying A, and he's saying that we will use 3V over 4L. Okay, from where, Hamza, just get this from the table up. Let's go to the table. Okay, it is what? Yes, there's something I didn't mention. Second resonance is very important thing. Second resonance, and we have closed tube. So these both things will specify for us which we will use, which equation in the table that. Okay, let's go. Close and the second resonance. Close and second resonance. Okay, where's the close? This is the close. Let me just close. I mean, erase whatever here. Okay. All right. So if you see here, this is the second resonance. Okay, which is closed also. As we have said, this is the first, second, and third. Even for the lower open tube, this is the first, second, third. Anyway. So now we are given what? We are given the L, if you remember, okay? We are given the L, this L, and we are given the velocity. And we asked to find the frequency. And Hamza is saying that, yes, you're right, Hamza. We will use this. We will use this one. We'll use this equation. This equation, we'll use it. Okay, so 3V over 4L. Okay, coming down, where is that? Oops, yeah, here. So you are helping me, Hamza. You're writing the formula. That's good. So now here, F will be 3V over, let's write it here because a little bit, maybe calculation in fee. Yeah, here, let's say here, F equals 3V over 4L. Okay, guys, just solve this. I need your answer. The calculation now quickly. F equals 3 times how much? What do we have the speed? 3 times 343, I think, yeah. Over 4 times. Now you have to convert from centimeter to meter. Why? Because the speed, which is 343, it is in meter. So when you just convert it, will be 0.15. So it means that this 0.15, it will be 15 over 100. It's equivalent to it. So we will use this way of formulation. Okay. So what we will have here, okay, somehow it's maybe complicated here. Let me just see. Oh, I will just make a second part here. So 100 will come up here, let's say. All right. Okay, it will be 3, 3, 4, 3, 0, 0. Because multiplied by what this 100 will come up here again. All right. And then this will equal to 4. Or let me just multiply it directly with the 15. 4 times 15, how much? It is 60. 60, yes, 60. Okay. So now 0 is 0, we're gone. Good. And 3 over 6, it is 2. So it will have 3, 4, 3, 0 over 2. Okay, so now if we divide, what we will get? Let's just try. 3 over 2, it will be 1. And here 17. And here, I think 1, and then 15. Good. Ah, yes, you're right. So it's C. Exactly. It is C, the answer. Great. Good job. Good job, guys. This is actually for the flat mirror. So let me explain first on the flat, then we will go to the other types of the mirrors. This is a flat mirror. First, that we have 3 types of mirrors. Okay, we have 3 types of mirrors. First one is a flat mirror, as you see here in the picture, and we have concave mirror, and we have convex mirror. Okay, the simplest case of the mirror is the flat one, as you see here. Okay, now what's happening here is that if you notice that we have 2 sides here, this side and this side. Okay, and this side now, you see now, this is the mirror, this is the object here, and these are lights coming from object, because now suppose this is a sun here, and sun, try just to bring the light into this object, and this object will reflect for sure the light. Reflected light are these lights. Okay, they will just crash with the mirror here, and again reflect it to the what? To the area around. For example, this is supposed that you are and standing, and you are watching here the mirror. What you will see here, the picture of this container here. Okay, but maybe you notice something here. What is this now? Why is this here actually? Okay, this is called actually imaginary side. If you see this dashed lines, it's called imaginary lines. Okay, just scientists do this for one reason, but just now keep in your mind, if you see dashed lines like this, it is imaginary picture, you can say. It is not real one here. So in the flat mirror, you will get imaginary or virtual. Okay, a virtual picture, not real one, because we have real, and we have imaginary. Okay, we will go deeply in this imaginary and real, and when we go just into concave and convex, will be more clear for you. Anyway, so now if you see in the flat mirror, the characteristic of the flat mirror will give you a picture that is equal to the object. This is now the image you will get, which is imaginary image in the mirror, and this is the object itself in the reality. Okay, so the one characteristic of the flat mirror, it's obvious that will give you an image that is equal in height and even in distance from the imaginary picture into the mirror, and from the object to the mirror. These distances are equal to each other. Everything in the flat mirror, put in your mind, are equal heights and distances from the mirror. Height, I mean here, for example, height of the object, this is the height, called h. And these are called d. If you see O, DO, it is distance of the object. If you see DI, it is imaginary, I from imaginary, distance of the imaginary. Okay, or I mean not imaginary, image. Just take it image, it's much better. Okay, and also the H, you notice that we have O, object, and also here we have H for this. Oops, H for this, it's called HI, which is the height of the image itself. Okay, so now if we just look at the question number 9, the image formed by a flat mirror appears. What do you think it will appear? And based on this now picture, now you see it is only one status here, you will notice. What I see here, Hamza. Okay, Hamza saying C. Okay, fine. I think Dua also, yes, Dua saying C. Good. Okay, what do you think? Oh, mashallah. Good. One. Yes, you're right. It is C. Why? Because virtual and also equal to objects in height, as we have said. Okay. Question number 12. A convex mirror. Let me just make it. Number 12. A convex mirror. Now we have a convex mirror. Okay. What do you think? Convex mirror, will be real or imaginary? What do you think? We said that concave have 3 cases, but yes, no, you're right. But convex only 1 case, and this case it is always imaginary. So this put in your mind it is imaginary. Yani here the question, it has to be negative di. Okay, and this is the way just how to get things. Okay, nice. Let's see, with a 2 meter focal length. So here it's F equal, now you see here it's meter, it's dealing with meter here. Okay, so now focal length is 2 meter, length is used to monitor parking lots. So if a car stops 6 meters away from it, okay, so the car stopped, so the car, it is the object itself. So we have DO, it has to be equals to 6 meters away from, okay, of the form image. And so what he wants here exactly, focal length is used to, so if the cars are, and then dimension of that, it means di. Yeah, I think he wants di here. Right. The image. Okay. Now, yes, same thing. Now we will utilize this 1 over F equal 1 over di or do, whatever, because it's plus 1 do. Okay, 1F, it is 1 over 2. Then di, we don't know it. Let's keep it here. Plus 1 over 6. Okay. Now, let's go here. 1 over di, let's keep it one side. And let's bring this here, 1 over 6 to there. So it will be minus 1 over 2, minus 1 over 6. Then if we make unity in the denominator, so we'll get what? We'll get
3 minus 1 over 6.
Yeah, yes, you're right. Good job. So it will be what? Here 3. Yeah.
Minus
3,
1.
Minus 1.
It will be 2 over 6. And then you just switch it. It will be 6 over 2, which is 3.
Yes, you are right. It will be 1 over 3. Then, as you said, that we have 1 over di, but we want di. So it will be di equals how much? 3.
And since it's imaginary, so it will be negative. So it's B.
Exactly. You're right. So it will be B. Because this negative, from where we get it? From the convex mirror. When it's sent convex mirror, it is negative because it will give us imaginary. Question number 20. An object is 4 centimeters from a convex lens. Okay. Now you see, now here is specifying for you, which is helping you. Real image. Good. So we expect that di, it is positive now, directly. But if he doesn't specify to you, خلاص, just solve it as it is. Just make it as positive. Okay. An object is 4 centimeters from a convex lens. It means that DO equal 4 centimeters. Okay. And we have a real, just put a line formed that is 4 centimeters from the lens. Also what? DI equals how much? 4 centimeters. And it is positive because it is real. Okay. So he's just asking about the F. So I think you know how just to get the solution here. What's the solution, guys? Not B, huh? It is C. Okay, yes, you're right. It is C actually. Because it will be what? As we know, 1 over F equals 1 over DI plus 1 over D naught. So it will be D naught or DO, it will be 1 over 4 plus di, which is 1 over 4. So it will be what? 2. 2 over 4, which is equal 1 over f. So it will be here half. Then if you just swap f up, so you have to swap them here also. So f will be 2. So it is C. Yes, right.